the delay. So yeah, so we are talking. I will talk about like provide a different, slightly different perspective to show how we turn this like a passive silicon nitride waveguide or integrated circuit working as a active component in our case. So first of all, I would like to give a very brief introduction to the motivation of this work. So we know the Erbium-doped fiber amplifier has been widely used in optical communication system. So it really represents the second generation of the driving force for these optical communications. So allow us to transmit a signal over like 1,000 of the kilometers long over like oceans. And so if you look at a lot of papers, so you can find out there's like a typical coherent communication link. Then you will find a lot of triangles, little triangles here. So these little triangles actually represent the Erbium-doped fiber amplifier. Okay, so the structure of the Erbium-doped amplifier is very simple. So you basically have like a the optic fiber doped with erbium ions. Okay, so then you excite the erbium ions, then the signal comes in, you cause a stimulate emission, then you can amplify the signal. Why is it important? Because the erbium ions has like the good emission wavelengths at near 1550 nanometers, perfectly matched with the lowest loss transmission band of optic fibers, and also the very unique electrical like a 4F shell structure, so allows you to have like very slow or gain dynamics. So in the end, you have a very good like immunity to the interchannel crosstalk. This is very different from the widely used semiconductor amplifier, which cannot amplify too many wavelengths at the same time. And also, it's the erbium ions are generally doped in a dielectric material, so it has better temperature stability compared to the semiconductor material. Of course, it gives you like a low noise figure, like approaching the 3 dB quantum noise figure limit for the phase insensitive application. So I'm not gonna like talk about the history of the EDFA in this case. So the general idea is that the Erbium-5 doped amplifier was invented in 1986. So after that, it was immediately used to replace the electrical repeater in the communication system. Okay. So, and the working principle of the Erbium-doped fiber amplifier is very simple. So once the erbium ions are doped in the optic fiber, then you can use the optic pump at 1480 nanometers or at 980 nanometers to pump the erbium ions into the excited state. Okay, so it has like a milliseconds long lifetime. Then you can relatively easily to like achieve a population inversion. Then you have net gain at the signal of interest when you have the signal coming in. So it has been widely used in optical communication nowadays, like for sensing, for test measurement equipment, and also the LiDAR application these days. So, but the issue is that if we look back, so it has been invented and developed for 30 or for 40 years, but now it's still mainly assembled by hand. So for example, if you open an EDFA box, so the fiber coil, the Erbium-doped fiber coil is still assembled by hand. So if you go to some like a product like a small form factor pluggable EDFA nowadays available, they have like the bending radius of like a centimeter. So it's also assembled by hand. So then it has the problem to really scale up the number of the channels for the different like physical multiplexing applications. And so if we, okay, so here like I provide a different like a perspective here. So if you look at the performance, the conventional Erbium-doped fiber amplifier can really give you a very good performance, but it's still like the benchtop size or it's a small OEM where it's a smaller size. But looking at from the other hand, so compared to the widely used semiconductor amplifier, which is very small, very compact, used for the communication transceiver, but it has like a stronger interchannel crosstalk, so it can amplify up to 4 channels nowadays in the Huawei or the IBM, the research lab, and it has a relatively high noise figure in this case. So we really, in the end, we really want to combine the best of the performance from the EDFA, but the small form factor from this integrated photonic circuit together to get like the very compact integrated circuit-based Erbium-doped device amplifier for laser. So if we can achieve this goal, then we can immediately miniaturize this Erbium-doped amplifier or the laser or even the model lock laser onto the chip. Okay, this gives us a lot of like a benefit. if you like a step back, actually, this is not a new, really new topic. It has been like extensively studied a long time ago. So, for example, if you look at this this review paper from Jonas Bradley's group, so you can really like give like a history perspective for these erbium-doped integrated devices already. And from the early on, so people try to basically integrate their erbium-doped fiber amplifier on the chip. So on the glass waveguide, so the cross section is relatively big, and the loss is also high. So and it's not really compatible with nowadays CMOS integrated photonic circuit platform. So recently, people try to use you use erbium dope like aluminum oxide and the telluride oxide material to form the waveguide. But you can only use these as a standalone devices. Okay. Well, more recently, the Sonia's group and Jonas Bradley's group start to look into we deposit this again like material or as a cladding onto the silicon nitride platform or even silicon and also the doped lithium nitride platform that can give us the on-chip erbium-doped fiber amplifier. But when you look at the performance, we really found the issue. So the typically reported the output power of this amplifier is typically in the like 1 milliwatt or even lower. For example, you can only achieve like 1 microwatt in a lithium nitride platform, although they claim very high gain. And the reason that probably because the waveguide length is not long enough and the propagation loss is relatively high and the dope concentration is not really high enough, also with a lot of quenching effect. So if you look at the simulation, you can find the typical like working regime for this waveguide. You can find out the waveguide loss is typically in like tens of dB per meter region, and the cooperative upconversion coefficient is relatively high. The cooperative upconversion gives you an effect to reduce the population inversion when you have like a high concentration and you pump it really hard. So it's another gain limiting factor. I'm not going to talk too much details about it. But for the target region, you really want to combine, the low loss property of the waveguide and also the lower cooperative upconversion coefficient when you have the high concentration of the erbium ions. So now we are trying to solve like these key challenges. First of all, we want to look into the loss, how to reduce the loss to start with, and the high doping or the ion doping approach that can give us a high concentration but a lower cooperative upconversion. And in the meantime, we want to achieve a large like a mode overlap factor. So let's start with the first ingredient. The first one is the silicon nitride platform we have been talking about in this conference very extensively. So we try to skip some of the key information, not key information. So the key information is that it has really large band gap, so it has a wide transparency window for photonics application, and also it has a high power handling up to 10 volt, and it has a lower to photon absorption, so we can pump this waveguide really strongly without causing too much damage. So at EPFL, we are developing the so-called photonic Damascene process. So instead of etching the silicon nitride film directly, we created like preform into the silicon oxide layer. Then we deposit the silicon nitride film into this preform, and then we use a mechanical polishing to smoothen the top surface. So another trick we are playing is actually is that we use the silicon material has like a transition temperature, a glass transition temperature around 1200 degree. So we can use a thermal reflow to smoothen the sidewall roughness. Then in the end, we can get a lower scattering loss from the sidewall. So in the end, in this platform, like recently, we can achieve the waveguide length up to 2 meters on a 5 millimeter by 5 millimeter photonic integrated circuits, and we can get a lowest loss approaching 1 dB per meter. So which set a very good baseline for this application. So there actually, for the low loss of silicon nitride, there's a lot of technology development on this by reducing the loss, adding more functional materials such as like aluminum nitride and the lithium nitride on this platform. More recently, we achieved this GaN media. So now I would show you how we merge, the low loss photonic circuit with a high concentration erbium ions in this platform. So to briefly discuss introduce this like a doping process, instead of like depositing the GaN doped oxide material as a cladding, so we inject the erbium ions into this silicon nitride directly by the erbium ions bombardment. Okay, so the erbium ions can be injected into this silicon nitride platform, and so you can see the green line shows the simulated the erbium ion distribution using the certain beam energy and the fluence. And the blue tracer shows the RBS measurement of the actual distribution of these erbium ions. It has a good overlap and it matches very well with the simulation. And it has a good overlap with the optical field so that we can get a larger mode area overlap factor, then the optical field can extract sufficient optical gain from these erbium ions. So this bombardment process, of course, will cause the damage and the defect in this waveguide. For example, before the implantation, the loss is typically 5 dB per meter. Then after implantation, you can see like absorption bands coming up like in this platform, which is good. But if you look at the background loss, it increased by more than 100 times. Okay, so this is going to be a big issue. So, but luckily, we can use the high temperature annealing at 1100 degree for 1 hour. We can recover this the low loss property in this platform. So the loss will drop back to the similar level as the platform before implantation. So that means we can maintain this loss. And also, we can use the selective doping by masking the different area using, for example, the 3 micron thick photoresist. So we can make sure like some of the passive part can be non-implanted. So in the end, if you compare the loss change before and after the implantation, the passive device of the loss can be maintained. Okay, so I will show you some example later on. So then, of course, once you get this sample, like once you merge this like a high energy, high concentration ion implantation and also low loss property, so you can get a really nice waveguide. So like with a different concentration, then you have a different lens for different purpose. So in general, we can achieve like a 30 dB on-chip net gain in this platform, and also you can see some like a fluctuation. This is simply because when the gain exceeds 30 dB, you start to have like a parasitic lasing formed by the FP cavity by the chip facet. So if you look at the amplification for CW light at 50 nanometers, the maximum output power we can achieve is more than 140 milliwatts. So which is really approaching the output power performance of the commercial EDFA. But there's still some issue. But the things we want to highlight is that, so this device is actually, for the first time, we can close the performance gap between the Erbium-doped Photonic integrated circuit amplifier and the Erbium-doped fiber amplifier. So in the end, if you look back at the potential of this device, so it's not only like a winning in terms of the form factor, it also wins in terms of the cost and also the scalability and also the performance. So we can think this can be like a really promising platform to replace some application of EDFA in the communication system or the other application, for example, in LiDAR. So I will. So how many minutes I can have?
Like 10 minutes.
Okay, sure. So in the next 10 minutes, I will talk about the application apart from the CW amplification. So one thing we would like to look into is to amplify the broadband signal. One of the example is the optical frequency comb generated in the silicon nitride passive current microcomb resonator. So in general, because it is a nonlinear process and also when it is generated, it has a larger resonance and the laser tuning. So the conversion efficiency for this comb from the pump power to these comb lines is fairly low. For example, it's typically less than 1%. For the 100 gigahertz comb line spacing in this case. So in any application of this optical frequency comb, you really need to use a EDFA afterwards, okay? So one of the application of the optical frequency comb, for example, if the comb line spacing is around like 20 or 50 gigahertz, which is RF photodetectable, and then you can use this to generate the microwaves. But if the power, the common line power is so low, that basically the noise performance will be shielded by this Photoshop noise, actually. So you really need to use the EDFA to amplify. Or for another application, for example, the optical communication, you have the optical frequency comb with 100 or 200 gigahertz FSR. You can use this as a WDM optical carrier to transmit your signal. But then again, you look at the link, there's a lot of small triangle along this link to amplify the comm line. So if we can replace, okay, the EDFA in this conversion applications with the Erbium-doped waveguide amplifier, we can immediately find applications. For example, in the microwave generation. So for example, in this case, we amplify the frequency comb generated from the passive silicon nitride waveguide from the different chip. We can get a similar performance as the commercial EDFA. But we notice there's some spikes coming out. This is simply because the regenerative amplification or the amplification enhancement and particular wavelengths because of the FP cavity of this chip. But compared to the case without optical amplification, the generated microwave, the frequency at high the phase noise at high frequency generated limited by the Photoshop noise. But if you have the amplification, then you can see we can achieve a similar phase noise performance compared to the case using fiber amplifier, which means our platform does not introduce too much impairment for this amplification process. Another demonstration is that we apply this waveguide amplifier into the communication link, so we can demonstrate more than 20 channel with a reliable transmission over a few kilometers long. So, but this is really a proof of concept demonstration that can show we can replace a certain application of EDFA. So the more exciting things for this platform is that we cannot really only use this as an amplifier, but if we can activate the integrated circuit onto the more complicated circuit, so we can activate the more interesting functionality. For example, the amplification of the soliton microcomb we showed in the previous slide. The frequency comb are from the different chip, but actually they are based on the same silicon nitride material. So essentially they can be integrated on the same chip. So recently we achieved this demonstration by integrating the passive current and microcomb resonator together with this erbium GaN element together. So we can achieve the on-chip generation of the microcomb and also the amplification of the comb. So we can deliver more than 10 milliwatt. Ideally, we can achieve 100 milliwatt output power from this optical comb. So the last example I would like to show is that so we can implement the high quality low noise CW laser in this platform. For example, we can easily use a loop mirror and a ring resonator as a filter to achieve a vernier laser for single laser lasing. So in this platform, again, we only activate the certain part, the GaN part in this spiral, we can achieve a good laser. So, for example, in this case, we formed a Fabry-Pro laser cavity, but with a vernier bandpass filter in the middle to select the mode. So for the longitudinal mode with a mode spacing of 200 MHz, we can still use a passive silicon nitride ring resonator to select the lasing mode. And we can get the low noise gain from this erbium-doped section. So in the end, we can form very low noise laser. We can achieve the intrinsic bandwidth down to 50 Hertz. Okay, and the laser can be tunable over 40 nanometers with a maximum output power of 17 milliwatt in the fiber. So of course, we can even improve the performance by optimizing the loss of this cavity. For example, we can reduce the insertion loss of the vernier filter inside the cavity, which is now 6 dB per round trip. So if we can reduce the cold cavity loss, it's possible to reduce the intrinsic bandwidth down to Hertz level or even sub-Hertz level. So in the end, I would like to summarize that using this erbium implantation to this passive silicon nitride integrated photonic circuit, we can achieve an on-chip waveguide amplifier more than 140 milliwatt with a 30 dB in on-chip net gain. And if we can also use this to implement more complicated the devices, for example, high power soliton generator and also laser. And nowadays, this process, the erbium ion implantation and the silicon nitride fabrication can be wafer scale and compatible with the foundry services. For example, Legentech will soon provide this service for this passive silicon nitride fabrication and also the implantation service probably in the future. So in the end, so in the last few slides, I would like to promote our lab-owned spin-off company, DeepLight, so who is commercializing the low noise laser with a fast frequency agility, which has a good application in LiDAR and the sensing platform. And now they have the booth in the exhibition area, so please feel free to visit them in the north building. And the other, we have another spin-off company, Luxtelligence, and we can provide the open access lithium niobate foundry service. So this platform, this foundry service can allow you to have like a deeply etched, tightly confined lithium niobate on insulator platform. Okay, so I think that's all. Thanks.